In part D of homework 1, we need to divide the CSTR into 20 smaller CSTRs in a series to mimic a flow reactor with batch mixing. Simulate and plot the concentration and temperature evolution of the 20 tanks over 2 minutes, starting with a concentration of 0.5 molar and temperature of 338.5 Kelvin in each tank, and maintaining constant inlet concentrations and temperature of 1 molar and 338.5 degrees Kelvin. Qualitatively explain the concentrations and temperature profiles. So the first half of this, such as dividing into 20 CSTRs, is very similar to part C, in which, so when after this clip is over, and I'm going to be starting to code out homework 1 part D, I'm going to be using a good amount of things we'd already derived and code we'd already made in homework part C, as these are very similar problems with slightly different end goals. So as you probably just saw, I'm going to cut these clips together, I just went over describing this problem here, which is part D of homework 1. So now we need to start actually coding. So we want to divide our CSTRs into 20 series that mimic a flow reactor. So what we're going to be doing is copying all these parameters from up here, from part B, which is what I took the liberty of doing that already. Also, now we need to add some of our parameters. So we need CA naught. We also need T naught, and then we're going to need a vector to add these all together. Vector 0 equals np dot r, and we're going to basically do these. So for CA and T naught, we're doing this because, as you can see here, we are going to change these values. So we're going to do CA equals np, I believe it's fill, or full. Ooh, I actually have to hit that first to make this all work. Dot full. We're going to be doing, let's double check, wait till this runs so we can see specifically what it wants. While we're waiting for that to run, I'm also going to explain. So I have homeworks B and C open because this is a combination of both. So I'm going to be referencing back, as we're going to need our mass and our material balances from both of those different, or their ODEs from both of those equations, from both of those homeworks. Let's see, np.full. Yep. And we want n, and we want 0.5, because that's what we're going to keep it at, or start it at, I believe. And we're just going to do n. And actually, we can double check this, because as I said, we have used this before. So it's going to be full, and then n, and then our value. So our value for CA naught is going to be starting with 0.5, which is all of them are going to start at 0.5, and all of them are going to start at 338.5 Kelvin. 338.5. So that should work. Actually, this is because we double checked, this is going to be parentheses. Now what we're going to be doing here is adding these together. So we're going to do, I believe this is CA naught, and then we do T naught. And let's see if this is broken. Okay, so what this is doing is kind of creating an array for us. Creates an array, a long array so we can do math. So now we're going to define our functions. So we're going to define, let's do T in, and we're going to do T, and what we want to return 338.5 Kelvin, and we're also going to define, that's fed, define CAN T, which is going to return a value of 1. And what we're doing here is creating these values, where over 2 minutes, starting with the starting concentration, we want to maintain constant inlet temperature and a concentration and temperature of 1 molar and 338.5 degrees Kelvin. So our Tn is going to be here, and so is our Can. So this is what these are setting up our values. And now this is basically making sure our values from the beginning are really basically stay at 0.0. So now we're going to define our right-hand side, in which is going to be t comma vector, and it might be, I believe it might be vex 0. Let's just keep it that way for now. It's not what I want to do. So first we're going to want to unpack, and so we're going to do CA naught comma T naught, I believe, equals our vector. And I could be doing this wrong. And now this is where we're going to go back to our two previous codes. So what we're going to be taking is first we want to take our energy and our mass balances from homework B, and we want to index them like in homework C. So I believe this is, let's see, homework 1B. We're going to copy all of that, and we will fix it later. So because this vector has temperature in it, we also are going to need to recalculate our K value. Like you see, it's the value of K. You can come over, Zach, it doesn't matter. We are going to do K naught times NP, ERT, and we're not done here because we're not returning these values. We need to give them life. So we are going to call this, we're going to have these separated because these calculate two different things. This is going to be, let's see, CA0 equal, CA0N, and then this is going to be T, and we're going to do CA1N equals, because this is our concentration from 1 to the n, and the concentration from 0 to n. Actually, let's double check how we named it in homework C, because this is exactly what we did here. TC1 underscore n. Okay. Just because I want to keep things a little bit consistent. 1 underscore n. And now we are going to Q, that's not what I want. Q minus V. So CA is going to, our first original value is always going to be CA in, right? Minus CA, which I believe is where I need to change this value. Call it to CA and T. Call this T. See, anything else is using specifically T, it is not. And then we are also going to create more space, just so we have a little bit more room, in which we do T, A, or T0N equals that, so ton, which is funny, and T to then 1 underscore N equals the same thing. Except there's going to be some small differences. And these differences are going to be in regards to our CA value, actually all of our CA value and also our K value, because we are, again, creating an array, and if K changes with temperature, we need to be also updating that value. So from 0 to n, if we look at homework 1C, when we have our 0, we do our original value, so CA n with respect to time, of course, minus C, and then we're going to, this C here from our homework is what we are designating as our right-hand side. So we're going to do that CA. We're going to do minus, sorry about the abrupt cut, I had some computer issues right there real quick. So we do need actually to change this to np.split vector, and then we want to do comma 2. And that's because we need, this is the wrong kind of vector. This is a different thing that we need. But now we can get back to doing this. So because this is 0, we want to index this as 0 times K, which is also 0, because again, K is also an iteration with our time, or not time, our temperature. And then also CA of 0. And now we need to change this. So this is a CA in, which we don't want that. We want this to be CA with a, I believe it is -1. Again, I will double check that real quick. And then that is a CA of probably N. So actually, before we start going too far, we can double check on homework 1B, homework 1C, where we actually use these values. So it's, yes, -1 and then 1 to nothing. So -1 and then 1 to nothing, which is basically saying we're starting at values 1, and this is basically calling the previous value. So our in minus our out. And then I believe K is very similar to CA, so much so I might just copy that because I'm lazy. V times V. Let's double check. Get one, what's that? A semicolon. Then, yeah, perfect. So that should work. And now we need to do T0n, which is a great name. So as we know, this is going to be Tn with respect to T. Well, this is going to be T -1. And then this is going to be 0. And this is going to be 1, our previous minus our now value. And then this is constant. This is not, so we need to do 0. And our K value is reliant on our temperature times CA. And I think we also have to call this CA value of, oh, this one will not be 0. That was a mistake on my part. Do 0. Then 1. And rho and C are constants. And then we need to do UA, rho V C. These are all constants. And then T, which this T value will be our current temperature, which will be 0, I believe. And then this will be also our current value, which will be 1 to the infinite, not infinity to n. So now we get to return our values. But one thing is we're going to actually change the names to D, because what this D is representing is change. So we're calling these to basically D for derivative, if I can ever get there. So now we are going to return, let's see if we can do it in an array or not. It'll yell at us if we can't. DC ALN, DC that, T ALN, and then DT1 to n, and see if it yells at us. Didn't yell at us. So now we can do solve IVP. So res equals solve IVP. Our function is going to be our right-hand side. Our t-span is going to be, well, we need to set a t-end. And our t-end is going to be 10 minutes. And you hashtag that out. And now, what's next? Then we do 0, comma t-end. Now our y0 is going to be a vector of, it's going to be vec 0, I believe, because that has our initial values, t0 and c0. Our method equals radow, and then dense output equals, of course, true. And we're going to see if this works. Let's see. Setting an array element with a sequence. Requested array has an inhomogeneous shape after one dimension. The detected shape was 4, comma, plus inhomogeneous part. So it's during our return fun rat. So there's something wrong with our array size, in which 40, which is what we want. So I'm a little turned around, as I think this should be working. So I'm going to double check why this is not right, and I'll be right back. So I ended up finding the issue. It's saying our array is in the right size, and that's due to the fact we did not do np-r here, our underscore. Oh, it's uppercase because caps locks is on. And what this is going to do is this is going to, let's see, it'll yell at me too much. It basically an array object of, and it allows us to do math with this. So that ends up getting boom shakalaka, we get that to go. So then we're going to want to do tplot, because now that we have our values, we want to plot them out. Tplot equals np dot linspace. Let's see, what is our values? Start 0, stop, tend, and how many do we want? Let's do 1 of 1 because we can. And now we also want to do something like, we want to split our variables, I believe. So we want to do something similar to here. So let's do, I don't know what to call this, we'll call this XYZ equals np dot split, and what are we going to split? Our array. Do res dot sol comma tplot, and then we're going to, what's our next thing? Array, indices or sections, you want 2 sections. 2 sections is 2, and then we're going to do axis of 0. Or do we have to do axis equals 0? Let's just put 0 for now, and if it yells at us, it'll yell at us. See, so that worked, which is crazy to me. So we're going to do fig equals figure, let's see, what's it say up here again? Make subplots. Make subplots. Right, now we're going to do for I in range of n, which is essentially how many we have up here, how many kanks. We need to do fig dot add underscore scatter. Oh, I did that right. We're going to do this twice because we want 2 arrays. We're going to want 2 different plots, so we probably want to do this. For example, if we look at our homework 1C video or work, we have, I was wrong. I did the code, I was wrong. Ag scatter, x equals tplot, y equals, for the first one, let's just do CA, which means we need to unpack that again, which is where I'm getting lost. We do x equals tplot, y equals t. Let's see, what's the next one? Oh man, that's so many. We're going to do mode equals lines. Yeah, I think this needs to be done. And we're going to do row equal 1, columns equal 2, and now we're going to copy this beautiful thing up. Instead we want call equal 1. We want name equal f apostrophe squiggly looking thing I. And what do you want to name this before? So this is going to be CA, or this is going to be CA. And now we're going to copy this. And we're going to have T. So what we're doing is we're naming our different iterations, I believe. So we want to figure out how the best way to unpack this. And I think we need to also do rows equals 1, or row equal 1, calls equal 2, just so it knows. And then rows. So it's probably rows, let's be honest. so invalid syntax. So I'm going to be right back when I figure out exactly the best way to unpack our CA and T from what we currently have, and if there's anything else I need to go and fix. So, I mean, I figured out where the syntax is, because we have two equal signs, but that is the right syntax. But I figured out why this was kind of, well, not kind of, very wrong. We have T plot for our temperature plot, because our lower T is always time, and we're going to have our C plot. And we also need to do what I had earlier, which axis is equal to 0. That should work. So now, instead of CA, we're going to do C plot. We're going to do I, comma, that. I don't know if mode lines is right, but at this point, if it isn't, I'll just get rid of it. I, comma, that, I think, should work. Or not. Let's see. Scattered calls. Did you mean fill? So there's something wrong with my columns. I'm going to get rid of this. I don't think it's needed. And see if this works. Nope, did I mean fill? So what they're saying is there's something wrong with no need to call raise on invalid property because we have it set up as a singular case of column. Invalid property specified for object of type plotly graph calls. So columns is not right. What do I mean fill? Let's see, when we do this, look at subplot, it has calls, rows, and calls. So calls is spelled right. Something is very wrong, and I just don't want to keep you guys on the video, so I'm going to Google/research why we are having this issue, and I'll be right back. And then hopefully by that point we will have our charts made and I can describe to you exactly what they mean, and we can get homework 1 done and over with. So last time we were getting this error, and I found out the reason is because I had something plural and it didn't need to be. So if we just do column, that ends up working, but now we need to print our value, print our charts. We're going to do fig. And fig here is going to print our values. So we have our CA, and we have our temperature. So now I need to explain to you what these graphs mean. So first I want you to think about, these are our TA and temperatures, in which our temperature, nice, mess up. Let's see, wait a second. CA naught, T naught. I got the order wrong. Yeah, no, I think I got the order wrong for, If I do this to, anyways, this may say CA naught, but this is actually T naught. This may say, so we're just going to switch this. We're going to switch T with CA, and we're going to switch this with T. .97, and then this is temperatures. Perfect. I just had these names switch around. So what you're looking at is kind of a cluster. So I'm going to explain. So what you want you to imagine is we first have 0.5 and it reaches steady state, 0.5 molarity at the same temperature. So we have our reaction going fine and dandy. Then at our original temperature we change. We change it to 330. As you can see here, very small change. We go from 0.5 to 1, which means it gives our reaction a lot more material to work with, which is why this temperature shoots up even though barely slightly. Then we go to the next temperature. CA1 we have a little bit less because it's being we have a little bit less our CA because it's being consumed and increasing our temperature. And then you kind of get that same feeling as you go out, because we have some more, as you can see, we have a higher temperature, but we end up having less CA3, T3, we have less. But then, so if we skip down, let's see, let's just keep going down, you're going to see a giant shift. So this is 6. Our temperatures shoot up as they continue to keep doing, and let's see, they keep going down. I'm just going to keep manually adding these one by one until we get the spike. So what this spike is, you can see our temperatures, our concentration goes really far down in the beginning, and then it spikes back up. And then our temperatures go down because our concentrations go down. So what happens is you can think of, we have 0.5 molarity right at the beginning. And then we spike it up with a consistent spike, which basically floods our reactors with this new material. So what this is doing is causing it to figure itself out. It is steadying itself out, figuring out what works best for the reactor, for the system. So as you can see, we have original, this is T19. It takes a while for that 1 molarity to go all the way through the system, which is why T19, or CA19, is down, 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 it's reacting, it's getting rid of all of its material, and at which point it's very low because it's eaten its material and there's less of it, so now it's reacting less and it's not heating up the tank, which is kind of why both of these look the inverse of each other. And then they spike up, that 1 molarity hits and it goes sky high, and we increase our temperature from 114 or 314 to 338. Same with our concentration, in which after that it levels itself off. It reaches its new happy state, which is what you end up seeing here. And the reason these are cascading is due to the fact that more of this material is getting reacted before it hits these certain tanks, or the certain reactors. And so I believe that actually answers all of part D. We divided our CSTR into 20 smaller CSTRs to mimic a flow reactor with backmixing. We simulated and plotted the concentration and temperature evolution of our 20 tanks over 2 minutes, starting with a concentration of 0.5 molarity and a temperature of 338.5 degrees Kelvin in each tank, so our C naughts. And then we are going to maintain an inlet concentration and temperature of 1 molarity and 338.5 degrees Kelvin, which is that shift I was talking about. And then we wanted to explain the concentration and temperature profiles. And that is exactly what we have here, which is what I was just explaining. So thank you, and I hope you enjoyed the video.